All right, chemistry students, welcome to our new unit. This is unit 6, um, stoichiometry. So stoichiometry is kind of a funky word. We're going to learn more about it, but at its heart, what it really means is has to do with molar ratios. That's really the heart of it. It's how to convert, um, how to move within a chemical equation in this a specific situation to calculate like the ratios of the different species in a chemical reaction. So what we're going to do is start off with molar ratios. At this point, you should have already been introduced to this topic from the POGL. So this should already be done. If you haven't, this is a good place to start. In class, we also probably talked about some recipes. So in a lot of ways, chemical equations are like recipes. And just like in a recipe, you have a ratio of different ingredients. So, if you're making like cookies, there's a ratio of the butter to the flour to the sugar. So like maybe 2 sticks of butter for every 1 cup of flour for every 1 cup of sugar, something like that. To, 1 tablespoon or teaspoon, not tablespoon of salt. Oh, that's too much. 1 like teaspoon of salt. And then like half a cup of chocolate chips or whatnot, or a third a cup of peanut butter, whatever. So in a lot of ways, that's the same thing as a chemical reaction. So let's get into that a little bit more. So molar ratios are the ratio of any two chemical species in a reaction. So it's the ratio of how these chemical species react to each other and how they're formed. This all comes from, excuse me, allergies. The coefficients from a balanced chemical reaction. And the units for this are always going to be moles to moles. So basically what happens when we're looking at a chemical reaction, for example, this one. So we have potassium phosphate is reacting with magnesium sulfate to form potassium sulfate and magnesium phosphate. This chemical reaction is balanced. And when looking at this, the way I interpret this is that for every 2 moles of potassium phosphate, it reacts with 3 moles of magnesium sulfate to form 3 moles of potassium sulfate and 1 mole of potassium phosphate. So maybe I'll even do like a quick little drawing of that. Why not? Let's grab some pens. What would be some good colors? Picking out some fun colors that would be, I think those will work. Maybe we'll throw in a red and like a yellow. We'll see if that shows up. Okay, so the way I can think about this is so there's 2 K3PO4s. There's this little, now they're not really all stuck together like that necessarily because they're aqueous, but this gives us at least an idea. There's going to be 3 MgSO4s. Okay, and it's going to produce 3 K2SO4s. And 1 magnesium phosphate. Okay, so that's like our chemical reaction. That's what's really happening here. So molar ratios are all about, you pick any 2 reactants or products, whatever it is, to kind of help you solve problems. So let's take a look at this, for example. Let's compare what's the molar ratio of potassium phosphate to magnesium sulfate. Okay, so the question what we're asking here is, what is the relationship between these 2 reactants? So the relationship is that for every 2 potassium phosphates, you're going to need to react with 3 magnesium sulfates. So in order for this ratio to work. So it's kind of like for every 1 cup of flour, you need 1 cup of sugar to make cookies. So the way that we would write the molar ratio in equality format would be for 2 K3, excuse me, PO4s, 2 moles, my apologies, for every 1 mole, or 3 moles, sorry, again, oof, of Sg4, MgSO4. Okay, this is a molar ratio, kind of in this equality format. We could also write it the opposite way. For every 3 moles of MgSO4, there are 2 moles of K3PO4. So these are both molar ratios. And it's the molar ratio that compares potassium phosphate to magnesium sulfate. Okay. We can pick any 2 chemical species to make a molar ratio. You can only ever compare 2 because it's a fraction. There's only a numerator and a denominator. It's an equality. So for example, maybe we want to compare magnesium sulfate to magnesium phosphate. Okay. So in this case, again, oh, just to go backwards for a second, I got these numbers from the balanced chemical equation. One thing to note about molar ratios is that they are specific to the reaction. So the molar mass is not like that. So the molar mass of potassium phosphate is always the same. It doesn't matter if you have a big pile of potassium phosphate or if it's in a reaction. The molar mass is just the molar mass of potassium phosphate. It's how many grams 1 mole of potassium phosphate weighs. Molar ratios are specific to the equation. So you don't have a molar ratio unless there is a balanced chemical reaction, and it is extremely specific to that reaction. Every time we have a new reaction, we're going to have a new molar masses, or molar ratios, pardon me. So that's something to keep in mind with this. They all come from these coefficients. This is the reason that we balance chemical equations. Well, one of them, so we can actually compare. So in this next example, we're trying to say, okay, like, how much magnesium sulfate do you need to produce magnesium phosphate? Or what's the connection between this reactant and this product? So in this case, we again go back to the equation. There is a 3 in front of magnesium sulfate. So that means that for every 3 moles of magnesium sulfate, we're going to produce 1 mole of magnesium phosphate. That's the relationship. Again, there's that invisible 1 over here that I don't ever like to draw because I hate ones. I hate drawing ones or writing in ones. So it's a 3-to-1 relationship. So for every 3 moles of magnesium sulfate, we're going to have produce 1 mole of magnesium phosphate. Or we could put it the opposite way. If we want 1 mole of magnesium phosphate, sorry, running out of space, but you get it. It's going to take 3 moles of magnesium sulfate. So that's the ratio. Okay, so molar ratios are another type of equality. So far we've learned about molar mass. So molar mass is the other kind of equality we have. That allows us to convert between grams and moles of a specific compound. Molar ratios are different in that they are not just for one specific compound. They are to help us understand the relationship between 2 different compounds or chemical species in a chemical reaction. The units are moles over moles. So if you notice, it's moles over moles. It's really important to write moles of what? Because all the units are the same, you can't just write 3 moles because it's 3 moles of what? Because otherwise it'd just be 3 moles over 1 mole. You're like, okay, well, what's the connection? Which one's which? So this is the kind of full proper way of writing this out. Okay, what we're going to do for the next set of notes is we're going to talk about how we use these. So we're going to do some mole-to-mole conversions. We're going to do mole-to-mass conversions and mass-to-mass conversions. But for right now, let's take a look at the unit packet. So your unit packet is here. It's the Unit 6 packet. And right now, you are now able to do page 1. So it's page 1. Let me go through the first problem with you just to kind of give you a little hint about this and how this works. Okay, so the first step is you have to have a balanced chemical reaction. So this is the chemical equation right here. In the second one, it's right here. This third one is not balanced. You have to balance it first. You always have to balance it first, but then you can use it. So we're going to write these molar ratios. So the first molar ratio is N2 to H2. So what we're going to do is look at the equation. We're going to find the nitrogen and the hydrogen. So according to this equation, for every 1 mole of nitrogen, it's going to react with 3 moles of hydrogen to produce 2 moles of ammonia. So the ratio of nitrogen to hydrogen is 1 mole of nitrogen to every 3 moles of hydrogen. Okay. B is asking the opposite. So this would be the flip. But it's the same idea. And again, it comes from here. There's an invisible little 1 in front of this nitrogen. There's a 3 here. That's where the 1 and 3 came from. And it's really important to keep them with the correct species. Okay. Let me just do one more just to give you that example. So let's now compare nitrogen to ammonia. So we go back to our equation. We're going to compare nitrogen and ammonia. It looks like for every 1 mole of nitrogen, we're going to produce 2 moles of ammonia. So this is a 1-to-2 ratio. Okay. So there's the answer for that. So I think at this point you should be able to kind of figure this out, hopefully. You can do the next one is just comparing hydrogen to ammonia. So looking at that one, it looks like we would be doing, for every 3 moles of hydrogen, you're going to produce 2 moles of ammonia. So again, that one looks like this. All right. And then D and F would just be like the opposites again. You just flip them over. And if you remember from equalities, as soon as you have the equality, you can always flip it over. So it's just whichever one is more useful. All right. So for you all, I think you all can handle the rest of these 2 problems. This shouldn't take you very, very, very long at all. And I will make sure that this answer key is available to you. I'll finish up working on it. And then what we'll do for next time is move on to actually solving some kinds of stoichiometry problems. But it's a weird word, stoichiometry, but really at its heart, it's all about these ratios. This is what's important. It's about connecting all of the different chemical species, the reactants and the products of a reaction together. How do they relate to each other? This is really important if you were trying to make ammonia. This is actually a really important reaction for history, in history. This is called the Haber cycle, there's a Haber process for making this. Ammonia is a really important fertilizer. And for a really long time in history, we couldn't really make our own ammonia. We had to rely on bacteria or like urine for that. So making ammonia was really important at one point. It's a complicated story that has a lot of moral ambiguity to it. There's bad and good things about it, but yeah, this was important at one point historically. So this is really important. If you want to make ammonia, you need to know how much nitrogen and how much hydrogen to add together to make the most amount of ammonia that you can and to make this really efficient. So if you don't add enough nitrogen, you're going to have a lot of leftover hydrogen that's just kind of wasted. And that's not like, you want to minimize your waste. So that's kind of like the main real application of this in terms of real life. That, yeah, in chemistry and in chemical synthesis, adding the correct amount of each reactant so that you can produce the optimal amount of product. In chemistry, this is like the math that lets us do pretty much everything. So this is the heart, the very, very first step of stoichiometry, which is like kind of the math that we're going to be doing, types of calculations we're going to be doing pretty much all year to some extent. I can tell you that in future units, we're going to learn a new concept, possibly some calculations relating to it, and then we're going to add stoichiometry into that, add this kind of math. So take a look at all this and we'll see how you do. And until then, I will, let me actually show you some videos that you can look at real quick, and then we'll go from there. This is my my YouTube channel. Once again, the playlist for Unit 6. This These three videos up here at the top could be very useful. This one is more like what we're going to cover in the next video, but you can start thinking about some of those. So I'm going to stop there. Thank you all, and we'll move on next with some calculations. There you go.